much like the pure components, the fundamental equation in terms of specific and specific variables, but only to include the C minus 1 independent mole fractions along with the specific entropy and the specific volume to determine the specific internal energy of the mixture. So the analogous equation in pure component is this. And then the general equation, which was here given by now would need to include the coefficient, the derivatives of the internal energy with respect to each of the C minus 1 mole fractions. So clearly the generalized chemical potential, the only C minus 1 of them is given by this. Obviously Zi not equal to J also means Z cannot be, I cannot be equal to C also, that's understood, because they are restricted only to the C minus 1 mole fraction. Right? So that is clear, that should be clear. So this is the general equation. And so if you restrict ourselves to homogeneous states, then we can, without encountering any technical problems, we can construct the various legendre transforms, much like we did for the pure component. The definition remains the same. The general equation can be easily shown to be sum is the same in all. Also, what we can see from these equations that you get alternate expressions for the generalized chemical potential, but they can also be expressed in terms of, for instance, E and so on, in terms of H and G. So the derivative is always with respect to the J mole fraction, the J generalized chemical potential. The variables which are kept fixed will depend on which function I choose to express the generalized chemical potential in terms of. Are there any questions? Okay. Further looking at the homogeneous states for the internal energy, we saw that E can be written again as homogeneous states of a mixture. The total internal energy will simply be the total number of moles. So N has the same meaning as for the pure component, the total number of moles, but now this is the sum over all the C mole numbers that you have to keep in mind. And we further find it convenient to express the specific internal energy, or the total internal energy, in terms of the total entropy, the total volume, and each of the C mole numbers. So now all the C mole numbers will come into play, because this is how we define the chemical potential of each component in the mixture. So from this, we easily show that dE by dS is simply dE by dS is P, and dE by dP is dE by dP minus P. The way forward came with the derivation of the expressions of the chemical potential, we had to distinguish between the formula for the first C minus 1 chemical potentials and the C chemical potential. The formula is somewhat different. You have to recognize that. And so I can then write, the derivation is not so much important, these are very central equations in the theory of mixtures, and it is quite surprising that very few of the books actually give these expressions. This is much like, for instance, here we had, you can ask what is the analogous equation for mixture. This is what it is. This will be given by again E plus PV minus PS plus minus sum over J to the 1 to C minus 1 Z J. This is what we get for I equal to 1 to C minus 1 of the chemical potential. But for mu C, we saw that this term which had came out of the delta Ij, sum over mu I star delta Ij, that will not come into the picture, because when you're differentiating dnj by dnc, the j is restricted to be between 1 to C minus 1. Right? Then dnj by dnc will always be 0. Whereas if you're restricting from I equal to 1 to C minus 1, then one of the i's may correspond to the j that you have chosen. So you get delta Ij. So that's how the distinction comes. Mu C will be all of this plus minus this sum. Even though these equations look quite complicated, you will see the inverse relation relating the generalized chemical potential to the chemical potential which we are all familiar with are quite strikingly simple. For instance, all I have to do is to subtract this. So I can take any one of the C minus 1 chemical potential. That's very important. If you take the C chemical potential minus mu C is 0. So mu I minus mu C, or I equal to 1 to C minus 1 is 1. Mu I star. So we now get an expression for mu I star. Each of these, there will be C minus 1 of them. So each generalized chemical potential is equal to the chemical potential of that component minus the chemical potential of the C component. This is a very important relation actually. So now actually we can go back, because when we introduced it, we didn't know anything more about the generalized chemical potential other than this obvious definition, variation of internal energy with respect to the home fact. Now I can replace this by, for homogeneous state, definitely I can replace this as so that we get well-known chemical potential into picture. So the mystery regarding the generalized chemical potential is sort of removed in this way. So now using this, suppose I substitute to any one of these C minus 1 relation. I can always use it here. I use it here. So I substitute this for mu I star. So I focus on any one of these 1 to C minus 1, right? And then we will see when mu I is plus PV minus PS plus minus sum over J to 1 to C minus 1 Zj times mu J minus mu. So I am just using what I have found by subtracting these two to get an explicit expression for the generalized chemical potential. Now I am using it. Now we derive a very important relation called the Gibbs equation, analogous to this for the analogous to this rather for the pure component. So that is for the pure component. I didn't confuse it with this. I defined for the mixture. Now for the pure component, mu is G. So now what we get is we cancel this. So if I now write E plus PV minus PS is equal to what, I can ask. I have to take everything to the other side. this would be mu c plus sum over j into 1 to c minus 1. So now I can see that this is equal to sum over j equal to 1 to c minus 1. I can write that separately. Plus mu c times 1 minus. So what is this term within the bracket? 1 minus. It's not 0. It is ZC. That's correct. ZC. I put only j equal to c minus 1, not j equal to 1 to c. That is very important. Be careful about the what it is summed. Sometimes it's convenient, even when using, as we will now see, even when using mole fractions. Sometimes we may want to introduce the ZC into the expression to make it compact, as we will now see. And even though we know that ZC is not independent of the other c minus 1 mole fraction, that's exactly what will happen. So this is ZC mu c, and this is j equal to 1 to c minus 1 Zj mu j. So we get this very famous relation attributed to Gibbs. Which is of course equal to G. So now the G, which was equal to the chemical, there was only one chemical potential for the pure component, was equal to that. Now we have shown that G for the homogeneous scale is simply the sum of all the C chemical potentials weighted by the corresponding mole fraction. It's a very important equation. This is what we have proved. So that's what I pointed out. Of course, I know that because while starting out, you can see you start out with only c minus 1. Now we've introduced the c mole fraction explicitly. There's no need to do that. But if you want to do it, then I have to leave it like this. You can figure out which one you find more convenient to remember. Either you want to write it like this, plus minus times 1 minus, or write it like this. This is really more convenient. I know that ZC is not independent of the other c minus 1 mole fraction, but it gives a very compact expression to easily remember. So G, which is equal to the chemical potential for a pure component, is now equal to sum over all the chemical potentials weighted by the corresponding mole fractions. Are there any questions on these derivations? So now we can see, just as we showed, that we can now, for instance, write it sort of differently here. E plus Pv minus Ps is for the pure component rather. Now I can write E as Ts minus Pv. I'm sorry, looking at the total internal energy. So pure component, total internal energy can be written as Ts minus Pv. Now we pointed out that this can also be obtained from this analogous expression for this would now be E is equal to the total internal energy to mixture is Es minus Pv plus sum over j equal to 1 to c Nj. Now, if we recall the Euler's theorem for a homogeneous function, we can now show that E for the mixture of lambda S, lambda B, same homogeneity holds now with respect to each one of the variables here, namely the total entropy, the total volume, and each of the C mole numbers. expression, much like we pointed out for the pure quantum. But however, you can regard this whole thing is more direct. I don't have to use that. I don't see why we have to use it directly, effectively through Euler's theorem in this special case. We see that the Euler's theorem is verified here, homogeneity of order 1, right? And you can write it out if you know Euler's theorem. I have got the same thing without using the Euler's theorem, right? But now I've got much more. These expressions cannot be got from anything resembling the Euler's theorem, right? So this is might be an indirect way to arrive at this, but we've got many more expressions on the way. Now, the same way as we did, we can also write this as A, because I know capital small a, specific Helmholtz free energy is E minus Px. So if I multiply both by m for the mixture, the total number of moles in the mixture, then I'm going to get capital A, the total Helmholtz free energy is total internal energy minus P times the total entropy. So I can from this write this as minus Pb plus sum over A equal to 1 to C. And then I have H, which is E plus Pb, is Es. And then G, which would simply be the simplest of the four expressions. It doesn't have any other term. We also pointed out why that is the case. For instance, if I want to write now the total entropy, the total internal energy, this is, we have already got this. A would be dB NC, H is SP, you can easily verify, and G would be so we pointed out, if you recall the discussion for the pure quantum, we said that these are both extensive properties. These are all extensive properties, all the molar. So those are common to all the four functions. So we are not going to worry about that. Now if we look at, so that's why they are all coming in the expression for the total thermodynamic potentials. However, here both are extensive, so we get a term for each one of them from the Euler's theorem. Here, temperature is not an extensive variable, so I don't get anything for that. It's only for the volume times the derivative of A with respect to volume. The same way for H, P is not an extensive variable, so I get only the term corresponding to S. So for G, both P and P are intensive variables. They don't have any extensive variable associated with them. By just scaling them by n, you don't get anything meaningful, right? So for that, there's no additional term other than the term corresponding to the chemical potentials or the mole numbers, right? Similarly, I can easily write the very well-known general equations in terms of extensive variables. These are very important, so we take the time to write them. Follow simply by the various definitions. The last terms are the same. Last term is the same all through, right? So now we also get then the expressions for the chemical potential. You can see how complicated this is in terms of the specific variables, right? But the chemical potential in terms of the extensive variables is very direct and simple, right? So that will mean that in many cases for mixtures, actually more convenient to work with the extensive variables, because anyway we are dealing with only homogeneous state and the mole numbers rather than the specific variables in the mole fractions. So mu I can be written as dE by dNi S Pnj not equal to I. Also equal to dA by dNi but the T, B, N, A naught equals I also equal to D, H. Also equal to dg by dni, d, b, n, a, I. The important point of these equations you should see, especially from the point of view of the criteria for equilibrium, which we derive from a pure component, the temperature, pressure, and chemical potential is uniform throughout the system in equilibrium. Right? So the same conditions can be extended to mixtures, where it will turn out temperature, pressure, and the chemical potential of each of the C components would have to be uniform throughout the system in equilibrium. So this will have implications for multi-phase equilibrium. Right? So now if you look at this, the significance of these equations are temperature, pressure, and chemical potential are the quantities that appear in the phase rule or the equality of the equilibrium criteria. And what we have done here, you can see, given a fundamental equation in the specific, because all temperature, pressure, chemical potential, they are all effectively intensive variables, none of them are extensive. Right? So we want to express them in terms of intensive and specific variables. You can see that as advantage. P is expressed in terms of dE by ds. P is expressed in terms of dE by dV. And since P, you have to refer to this in this equation. Similarly, P. Everything you can see in this equation, the chemical potential, any of the chemical potential you can take, either I equal to 1 to C minus 1 or the C chemical, everything can be obtained from E and its derivatives. So once the fundamental equation is given, E is there, P is just a derivative of V with respect to V negative. Again, E is the derivative of V with respect to S. S is a natural variable. And Ui star is nothing but the derivative of V with respect to Zi, right? That can also be obtained once E is given. Everything what we have done is express the temperature, pressure, and chemical potential in terms of the fundamental equation and its derivatives, right? The same way, the slight manipulation of this very same equation, you can show each of them can also be expressed in terms of the other fundamental equations, namely A, the specific Helmholtz field, the specific enthalpy, and the specific Gibbs field. All you have to do is for this here, I will simply write this as A. I'll just give it as an example. Now for A, right, T is a natural variable, so I don't have to worry about this. Now P is also minus dA by dV. So P is known from A. B is again a natural variable. We have shown that Ui star is also or can also be expressed in terms of the derivative of A with respect to the corresponding mode factor. So these similarly we can do for H and G and then show that given any of these four fundamental equations in terms of the specific variable, the temperature, pressure, and chemical potential can be expressed in terms of those variables that appear in the fundamental equation and the various derivatives, right, and so on. So this will lead to the derivation of the phase rule for a multi-component, multi-phase mixture, which we will take up later. But now if you see other questions about all of these equations and the derivation. Of course, to get to this is probably the most difficult. I won't worry too much if you didn't follow all the steps. What I don't expect you to remember these expressions, but some of those other expressions are very important and you should remember, especially the Gibbs equation and also the definitions of A, H and G you now see effectively remain the same for a mixture. Right? So now you can see on comparing these four equations, clearly this is the most compact expression of the total quantity because there are just C terms in it, the chemical potentials and the mole numbers. Whereas when we are doing for this, E, A and H and so on, some other terms come in. Now the question architects and engineers, because we want to have everything in compact, and temperature and pressure are natural variables, I mean more natural for engineers than for physicists. So you can ask, can I obtain a similar expression, compact expression, just see them, for these other quantities, or in fact for that matter any extensive property, right? So the answer to that is in the form of another very important quantity that is introduced in many of the textbooks, which is the partial molar property associated with an extensive variable. Any extensive variable you take, let's say take the internal energy, right? The internal energy, its natural variables are Sp and the mole numbers. But if you want an expression like this for the internal energy, we see that the critical thing here is that G is dependent there only on the intensive variables apart from the C extensive mole numbers. Right? So in the same way, I can always look at a representation of E in terms of the temperature, pressure and the C mole numbers. Then it's possible to show using in fact the special case of the Euler's theorem that E then can be written as J equal to 1 to C Mj dE by dNj dP in A not equal to J. This is identical to that, because if you recognize what the mu J is, it is nothing but dP by dN. I have that here, dE by dNi dP. So we can argue that if I introduce this derivative with respect to Nj, so now I define this as the partial molar internal energy with respect to component J. There will be C such quantity, so I introduce Ej partial molar. Notation is somewhat different because some books put a bar on top of it. For me, it doesn't suggest anything. So Ej, when I put, if I don't put anything, Ej would correspond to the pure component J in its pure state, not in the presence of other components, but its own pure state at a particular temperature and pressure. That's a specific internal energy, we know that. Right? But here, the moment I put Em, it automatically refers to a mixture. It's a partial molar property, and it corresponds to only a mixture. If you are not confused, you can add a superscript there. In fact, I should probably put here E mix this. But it's very clear from the context. The moment I put E as a function of the mole numbers, all the C mole numbers, if you understand that it refers to a mixture, right? So when I put this, so the definition of this is dE by dNj. So for any extensive variable, in fact one of the most commonly studied extensive properties in terms of its partial molar property is the volume. So Vj. So you can replace it by anything. So you can replace it, for instance, by H, then you have to replace this by H. And if you want S, then make this S, and so on. So you think of all possible partial. So partial molar property is associated with an extensive property. Any extensive property, if we have several examples, the internal energy, the total internal energy, the total entropy, total volume, the total enthalpy, the total Gibbs free energy, total Helmholtz free energy. All of these are extensive properties. For each one of them, I can define a partial molar property for each component in the mixture. Right? If I do that, then I get this compact representation. Accomplished what I wanted, which I found here to be quite convenient for the Gibbs free energy. Important thing to remember is that this is not equal to except except when the extensive property is the Gibbs free energy. The Gibbs free energy, right? Except when extensive properties is equal to G. G. Maybe here I should put a mixture. All along we should put a mixture. Because this will become very important, because often we will relate the mixture chemical with the chemical potential of a component J in the mixture. We should try to compare it with the chemical potential of the component in its pure state at the same temperature and pressure or whatever. Right? So in those cases we will definitely distinguish the mixture quantity with the superscript mix. Are there any questions? So we have introduced most of the important quantities other than the fugacity of a component in a mixture we will introduce later. Now the problem we can pose is very similar to what we did for the pure component. If you look at the pure component, one of the major question we raised was, suppose I take a property U, a specific property, how to calculate the changes in this between two states, right? That is, for instance, for a pure component, this could be U of T2 P2 minus U of, and we also related the change in properties, some specific quantities like the internal energy and the entropy and all that, they were related to heat and work interactions in specific processes. We also derived some of these relations. So now, instead of pure components, we could have a mixture undergoing these processes. So we need obviously be able to calculate the change in property of the mixture. Right? So just pure methane, you could have methane in combination with some other butane or something undergoing the same. It is more common in chemical engineering. So we need to be able to calculate that, calculate the change in property of a mixture now from one state to another. So for that again we need to, if you look at the procedure we adopted, first we calculated the various differential coefficients of the various properties like E, H and so on with respect to B, E and so on, differential coefficients. So we can use them when integrating. But it so happens that the formula for mixtures can be very easily inferred from the formula for pure component, and I will now outline what these formula are and how to infer from pure component. So for that, we will restrict ourselves again to gas mixture, because there also we said we will be having phase change, right? We could we have to be very careful in adding or subtracting the changes due to phase change. So we focus on the gas phase, and there we found the departure function serve the useful purpose, because by using the departure function we could relate the changes in properties by using the ideal gas specific heats into the picture, because those are readily available. Right? So now let me take as an example what I mean by this kind of a change or inferring the mixture equation. You should be careful which equation and how you have to modify it. For instance, let me take a formula for pure component. Departure function. So we are focusing now on gas mixtures undergoing changes of state and how to calculate the changes in property. Later on we will see how to do the same thing when phase changes occur for mixtures. So let's take this. This is the formula I have. Integral infinity to V, or maybe I can put a specific temperature and pressure. This is how we add it. T1 T2 what we have, right? So now I will tell you, suppose I want to extend it to mixtures. I want to know what is the corresponding departure function for a mixture now of arbitrary C number of components. Then I put H mix minus H. Now this will become, instead of IG, it will become the ideal gas mixture, which is something we haven't introduced so far, which we have to introduce. So I am just pointing out the trick to write the departure function expression for mixtures from the pure component molar part. This remains as it is. Only now the Z obviously is a compressibility factor. Is here it is PV1 by RT1. Here it is also PV1 by RT1, except that the specific volume now corresponds to the specific volume of a mixture. It is defined in the same way, because we are dealing with only homogeneous states of mixtures. So volume by total number of moles will give the specific volume of the mixture. That's all. Because now becomes the mixture. Temperature, of course, we can put mixed here also, but we know we are talking about mixture. That's T1 is the temperature of the mixture. However, important thing is that T1, P1, this will now depend, because we have used Z for the mole fraction, we can now shift to Y, because we are going to use only this for gas mixtures, right? So I can maybe make that, make it Y, and I'll put 1 as a superscript to indicate that, because Y itself has Y1, Y2 to YC minus 1. So that is, we have already used it for subscript. So to indicate that this corresponds to a particular state with certain specific values of the mole fractions, I can put that as 1. So this is the expansion of this as Y1. This refers to component. This refers to the state, a particular state. This will remain 1. I'm introducing this as a mole fraction vector for compactness. Right? I'm picking a particular, as I've always done, let's pick a particular state T1, P1, and having certain mole fractions Y1, 1, Y2, 1, Y3, 1, all the way up to Y. Because those will also now come as variables in the mixture properties, and those also have to be specified. We could have a change of state where one state has a certain mole fraction that will happen when there are reactions, but typically we might not consider that. So the simplest of cases, normally where there's no reaction and just a change of state due to a certain mechanical or a thermal process, we might often deal with only changes of state where there are no changes in mole fractions or the composition of the mixture. So the change would only be the temperature and pressure. So then plus infinity, obviously this would correspond now to the mixture. T1, now dP not only will depend on, the interval will continue to be over the volume, but now the pressure will also be determined not only by the specific volume and the temperature, but also by the mole fraction, right? So that also have to come into the equation of state. But the integration is only over the volume, so you don't have to worry about it. You have to give me a specific, if we want to change in state from T1, P1, Y1 to more typically T2, P2 and Y1. Let's not introduce complication to change of composition. Then I have to write this whole expression for T2 and P2, and obviously T would also change, right? So now there are many new ideas that I have introduced which we have not covered. One is the concept of an ideal gas mixture. Of course, the proof of this, it can be proved, but I am not going to get into the proof. Proof is slightly more involved. You can ask how you can, just by inspection, why should the form of the, with these changes, when many books don't even mention that this has to be correspond to an ideal gas mixture. So by everything they put a knot. We don't know what this knot represents. So we have to be very careful. And how this is in fact possible. Right? Many books write as if it is obvious. I don't find anything obvious, but it does seem to be correct, which I have verified. Right? So now, one important thing is the concept of ideal gas mixture. Another is how is now the equation of state going to look like for a mixture? Possibly that assumption that I am going to make now probably also contributes to this connection between the pure component and the mixture. Right? So the mixture equation of state, we will say that we will just adopt all the equation of state that have been considered for pure component, and we will take the simplest of them, maybe the van der Waals. So now let us say I am considering a mixture of, this is a pure component, let's say methane, and then I have X, right, methane, let's say. So A would correspond to A of methane, and B would also correspond to B of methane. We have seen how to get it from the critical constant. Now we assume here that the form, if I am using van der Waals, if I don't find van der Waals useful, I go to Peng-Robinson. Whatever I do, I will retain the same form. Form is not changing. So for a mixture, P of course is the P of the mixture. If you want, I can put that. Everywhere I can put, but where there is confusion, most important is that suppose now I have a mixture of methane and butane, let's say, or propane. Now I will use the same equation of state. So this is all very clear. I don't have to confuse it further. It's obviously going to correspond to specific volume of the mixture. But now, what I do is I relate the mixture parameters to the pure component parameters. Right? Let's say I call this 1 and 2 by what are known as mixing rules. Now the most common mixing rules I like for a binary mixture would be that we mix. There are many, there's a lot of research done on mixing rules. Many people focus their entire life on mixing rules, find suitable mixing rules that will predict properties of mixture. There's no agreement or no rational way of doing it. Right? It's somewhat empirical. So some of the common mixing rules used are J equal to 1. In fact, I can even write it for C components. Bj, Zj, or if you want Yj. But it applies to any mixture, can even apply to a liquid mixture. Then you choose the corresponding mole fraction of the component in the liquid phase, right? Bj will maybe let's make it very gentle. So now you can see how the dependence of the P on the mole fraction is coming in. It is coming through the parameters themselves. Now they are no longer constant. The parameters for the Peng-Robinson or the van der Waals, they were at best functions of temperature for a pure component. Right? But here now they will be a function of the composition also. Right? So a very famous mixing rule for the these are the simplest. So Bj is the pure component van der Waals constant here for the component J that we know how to find. Right? So the mixture B is found by simply taking a weighted average of that, and this would often be written like this, where Aij, simplest again form is square root of Aij. This is more like an average. This is a somewhat more complicated one. Aij, Zi, Zj, but Aij is obviously here the way it is defined is equal to Aj, and simply taken to be the geometric mean of the individual parameters of the two components I and J. So you take two components at a time, form the Aij, and then form the sum. Right? So clearly this is also now a function of Z, even for a van der Waals. So that is how now the equation of scale will become dependent on the composition. So that's where it comes in. So we take up these points. First is what are the properties of the ideal gas mixture. So what we will do is, if I want to calculate for instance delta H, I will do the same trick. That's all. So this I know how to calculate from the equation of state for the mixture. Obviously we have to go and find the volume by solving the cubic equation of state. And this I need to know the properties of the ideal gas mixture, which can be related to specific heats and so on. So the procedure for the mixtures is identical to that of the pure component. These two important ideas, one, the properties of the ideal gas mixture would come in, and you should know how to handle equations of state for a mixture. With these two simple ideas, which are mainly extensions of the idea of ideal gas for pure component and the equation of state for the pure component, we can calculate all the property changes for gas mixtures for a mixture. We'll see how to do that in some specific cases in the next class.